안녕하십니까? Nicolas입니다 and welcome to the second video on this series where we are becoming blockchain developers. Before we start, make sure you watch our previous video that we did on this series to understand all the concepts and the fundamentals required for blockchain development. Because today's video is all about practice. What we're going to do today is we're going to write a smart contract for a fundraising application like Wadis or Kickstarter using Solidity, a very easy to use and learn smart contract programming language. And using all that node, which are the sponsors of this video, we are going to learn how to deploy our code to multiple chains in record time. As always, please remember that if I mention any project on this video, I am doing so for educational purposes only. Now let's get started writing our first smart contract. As we said on the previous video, you can write your smart contracts in a variety of languages. The one that is the most used and the one that I believe has the biggest community out there is Solidity. Solidity is a programming language influenced by C++, JavaScript, and Python. That means that it has C++-like syntax, which means that if you know TypeScript, JavaScript, C#, Java, you're going to feel right at home. A smart contract sounds very scary, but actually it's just a class, like a class that you would find in Java or C# or TypeScript or JavaScript or even Python. Smart contracts have a constructor, they have properties, and they have methods. This means that if you know OOP, you're going to fly when learning Solidity. To create a smart contract inside of a file called fundraising.sol, that sol being the extension for Solidity files, we are going to write this line of code at the start of our file. Here we are locking the version of the compiler to make sure that our code is not compiled by a compiler with a higher version number and maybe breaking changes. We do this because Solidity changes fast and things break often. Now we're going to create a smart contract called fundraising by creating a class called fundraising, except that instead of using the keyword class, we're going to use the keyword contract. Our fundraising contract is going to have properties like the owner of the project, which is the person that is trying to raise money, a target amount, which is the money that they're trying to collect, a list of all the people that donated to the project and how much their donation was, the accumulated amount of total donations, and finally a deadline, the amount of time the project has to reach the target. If the project is over and the total amount of donations is more or equals than the target amount, then the money collected is going to be transferred to the owner of the project. But if the campaign is over and the amount of donations is less than the target amount, then the people that donated to the project are going to be able to get a full refund. So let's write these properties into code by first specifying the type of the property, then if it's public or private, then the name, and optionally an initial value. We start with the target amount. This will be an unsigned integer, which means a non-negative number with a size of 256 bits, which is a size that can hold a number as big as this. Then we're going to add a property called owner. It's also public and the type is of type address, which looks like a string, but it has the correct format to be an Ethereum address so we can send money to it. This is the address of the wallet of the owner of the project where all the funds will go if the campaign is successful. Now we're going to create a public mapping of the addresses and the amounts of the people that donated to the campaign, and we will call this donation. You can imagine a mapping like a hash table or a dictionary, where the key is the address of the person that donated and the value is how much money they donated. It could look something like this. Now we're going to add the total amount that the campaign has raised, and we're going to initialize it to 0. And finally, we're going to add a finish time property that would hold the date in seconds when the campaign will end. Here, as you can see, we're using a variable called block, which is an object that we didn't define before. Block will be defined by the EVM, the Ethereum virtual machine, when we deploy our contract. It will contain the information of the block that is uploading our contract to the network. Blocks have a time stamped, which is the date when they were created in seconds. So we are taking that date and we're adding 2 weeks to it. This means our campaign will last 2 weeks. The week unit is also provided for us by the EVM. Next up, we will define the constructor of our class or contract. Inside of the constructor is where we will initialize the target amount and the owner of the contract properties that haven't been initialized yet. The constructor will take one argument, it is a number and it will be called underscore target amount. We will then set the target amount property of our class to be equals to the underscore target amount. This means we will allow the owner of the project to specify how much money their campaign wants to collect when the contract is being deployed. Now, to set the owner of our contract, we just have to add this line of code. Now, this MSG or message object is very similar to the block object that we used before. We did not define them at all, but they will be defined when our code runs inside of the EVM. In this case, msg.sender or message sender will be the address of the actor that is creating the contract. And we are done with the constructor and the properties. As you can see, so far it's very easy to understand. Now we're gonna move on to the methods of our contract. We have to remember from the previous video that the EVM compatible blockchains have two kinds of accounts. One is an externally owned account, EOA, or a human account, and the other one is a contract account, which is controlled by code. Now, EOAs, aka humans, can send money to contract accounts, and also contract accounts can transfer money to EOAs. Because we want humans to be able to send code to the contract account, and we also want to run some code when that happens, because we have to increase the counter of how much money we have, and we also have to write down the address and the donation in our donation list so we can maybe issue a refund later, we are going to write a function called receive. And we have to say that this function is external, which means it can only be called from outside of the contract. And we will finally add the payable modifier to it to indicate that this function can receive money. And that's it. Now when somebody sends money to our contract, the receive function will run. In the receive function, we are first going to check if our campaign is not over yet. For this, we will use the require function. This is a function that checks if a condition is true. And if it isn't, it will throw an error with a message and it will stop the execution of our code. So in the receive function, we're going to say that we require the block timestamp, which is a date, to be smaller than the finish date of our contract. If the block timestamp is of a bigger value, that means that the current date when this code is being called is after the finishing date of our contract. If that's true, we will show an error saying that this campaign is over. As you can see here, we are using the block global variable again, but inside of the receive function, the block that timestamp will be the date of the block that is being used to save the transaction created when a user sends money to our contract. If a human is sending money to our contract and the campaign isn't over, we are going to add the address of the human that is sending us the money and the amount of money being sent to our donations mapping. We are also going to increase the raised amount counter. Again, we are using the global variable MSG and the property sender to know who is sending money to the contract. And you are using MSG.value to know how much money they are sending to the contract. We then save this info in our mapping with the sender as the key and the amount of money as the value. And we're doing plus equals instead of equals because people can donate more than one time if they want to. Next up, let's write the function to release the funds to the owner of the campaign if the campaign is successful. For this, let's create a function called withdraw donations. Withdraw donations will check if the person that is calling this function is the same person that created the contract by checking the message.sender with the owner that we defined on the constructor before. If they are not the same, it will throw an error. And for this, we also use require. Now we have to check if the raised amount is more than or equals to the target of the campaign. And if it isn't, we're going to throw an error using require again. The last check of this function is to see if the campaign is not over yet. If it isn't over, we won't allow the withdrawal to happen. If all these conditions are true, if the person calling the withdraw donations function is the owner of the contract, if the raised amount is more than or equals than the target amount, and if the campaign has finished, we will release the funds to the owner of the contract. We do this by calling the payable function with the address of the owner that we set in our constructor. And then we call the transfer function to transfer the value of the raised amount variable that is keeping track of how much money has been sent to our contract. Now we need to write a function to give a refund to the people that donated to our campaign if the campaign is over and if the campaign didn't reach the target amount. And using require again, we will check if the campaign reached its goal. If it did, then there won't be a refund as well. And finally, we will check if the user asking for a refund is on the donations list. If all these conditions are true, if the campaign is over and if it didn't reach the goal, and if the user that is asking for the refund did donate to the campaign, we will put the amount of money that the user donated inside of a variable. Then we will update our donations list to make sure that the same user cannot ask for a refund twice. And finally, we will transfer the donated money to the user, giving them a full refund. And we are done. Now it's time to deploy our contract. For this video, we are going to use Hardhat, which, as you will see, is very easy to use. After we run npm init inside of an empty folder, we are going to run this command to install all the things that we need to install. Then we will run npx hardhat to create a project, and we will select the option to create an empty hardhat config.js. We will open hardhat.config.js and we'll make sure that the Solidity version is the same as the one in the pragma of our contract. If it isn't, we will make them match, and we will also import other things that we need for later. Then we will create a folder called contracts, and there we will put the fundraising.sol smart contract that we wrote before. Now we need to create an account on the blockchain. This is to be able to deploy our contract, but also to be able to receive the donations to our wallet. For this, we will install the MetaMask extension in our browser. Because deploying a contract to the Ethereum network costs real money, we're going to instead deploy our contract in a test network where we can use test money to pay for our test transactions. On this test network, the cryptocurrency Ether has no value. Even though it has no value in the testnet, we still have to get some. For this, we're going to go to the all.node faucet, which is a service where all.node will send you test money to your test wallet. After we go to the Ethereum faucet, we will select the Goerli network, which is the testnet where we are going to deploy our contract, and we will paste the wallet of the address that we created in MetaMask. After a couple of minutes, we can go back to MetaMask, and after selecting the Goerli network, we can see that our test money has arrived. To deploy our contract, we of course have to talk to the Ethereum network. And for this, we're going to use all.node, so we don't have to download anything, and instead we can just use their API. After we log into all.node, in our dashboard, we will create a new project and select the Ethereum network. After the project is created, we will see multiple RPC URLs. We will copy the Goerli RPC URL. We will head back to our hardhat config.js and we will modify our code a little bit to tell Hardhat that we want to talk to Goerli by putting this code on the file. As you remember, thanks to the awesome people of all.node, we received test money in our test wallet, and we saw that in MetaMask. This means MetaMask is the only one that is currently controlling that wallet. What I want to do now is I want to allow Hardhat to control that wallet as well. To allow Hardhat to control that account, we're going to go back to MetaMask and we will click on account details, and then we will click on export private key. This will show you a key that can be used to completely control your account. You should not show this to anyone, and you should not upload this key to GitHub. For this tutorial, we're going to copy-paste it right into the code, but in real life, you should use a .env environment file. Inside of the Goerli object, we will copy-paste our private key inside of an account array. Now we are finally done, the setup is complete, and we can finally write the code to deploy our contract. Inside of a folder called script, let's create a file called deploy.js and put this code in there. It's pretty easy to understand what's going on here, so let's go through that. Using Ethers, which is a JavaScript library to interact with Ethereum, we are grabbing the fundraising contract, we are compiling that contract, and then we are deploying it with one argument. This is the argument that the constructor in our contract needs. As you remember, that argument is the target amount of money that we want to raise in our campaign. As you can also see, that argument is a pretty big number, and this is because just like $1 is divided in 100 cents, 1 Bitcoin is divided in 100 million Satoshis, and 1 Ether is divided in 1 quintillion way. So that number is way. That's the unit, and those ways equal to 100 Ether, which is the amount of money that I want my campaign to receive. So if I want to raise 100 Ether for my fundraising campaign, I need to create my contract with that value on way, which is this number right here. We can of course use Ethers to help us format this number. Now, the last thing that we're doing on this code is that after our contract is deployed, we are console logging the address of the contract on the blockchain so we can go and check it out on the blockchain explorer. To deploy our contract, we're finally going to run this command right here, and if everything goes well, we will see the address of our contract in our console. Now, all we have to do is go to the blockchain explorer of the Go Early testnet and search for the address of our contract. As we will see, it will show up there, which means our contract is deployed. And if we click on the contract tab, we will see our contract code compiled to bytecode. The bytecode is what the EVM will execute. And that's it. Our contract is live. The campaign is running. Now let's put some money in our contract. Let's donate to this campaign. Because the contract, as you can see, is just an account with an address like a human account, we can just send money to it with our wallet. Let's copy the address of our contract, go to MetaMask and send some money to it. As you will see, the contract received some money. You can see in the blockchain explorer, the contract has a balance and that balance increased. Now let's see if our receive function actually ran when the contract received money. For this, we're going to interact with our contract via JavaScript. So let's create a new task in the hardhat.config.js. Inside of that task, we will get our account and we will also paste the address of our contract. Now, the last thing we need to be able to interact with this contract using JavaScript is something called the ABI. It is very similar to API that we use to communicate with a server. In this case, we use the ABI to communicate with the binary contract. To get the ABI of our contract, we will go to the artifacts folder and then contracts, and then we will find fundraising.json. There we will see the ABI, and as you can see, it's just a JSON description of our contract, the functions, the return values, and the argument types. We will copy-paste this ABI into our task in the hardhat.config.js. And now we are ready to interact with our contract. All we have to do is send the address of the contract, the ABI, and the account of the human that wants to interact with it. And now we can call any method in our contract using JavaScript. For example, we can check what is the target amount of our contract, and we can also check to see how much it has been donated so far. To execute this task, all we have to do is run this command in our console. And if it works, we're going to see the target amount of this contract and also the amount that the contract currently has. And that's it. We are done. We did it. Now, if you wanted to deploy this smart contract to another EVM blockchain like Polygon or Avalanche, all we have to do is create a new project on the all.node dashboard to get a free API key, then get test money from the all.node faucet, and add the network URL to our hardhat configuration file. Thank you to all.node for sponsoring this video, and thank you for watching it. Please let me know in the comments if you would like me to keep making blockchain development tutorials, like maybe, for example, adding a frontend to this application using React, or maybe cloning our own decentralized exchange or NFT marketplace. Thank you so much for watching this video. Let me know in the comments, what do you think of this video? Do you have any questions? I'm gonna be looking at them right now. As always, stay free, stay happy, eat kimchi, 감사합니다, 사랑해요. See you on the next one. Bye bye.